Okay, so we're going to talk about fluids. Okay, everything in our life happens in fluids, so we want to understand fluids. What are fluids? Things that float. So things that gases and liquids are both fluids. Okay, so that's what we'll talk about. What is the difference? You see, gas molecules, they have lots of space between them. In fact, if that is the size of the gas molecule, the average space between gas molecules is about 10 times their size. So if you hold up your fist, the distance between gas molecules, if a gas molecule is the size of the fist, your fist, the distance between them is your arm's length. Okay? So they have plenty of space to move around freely. They can speed up. The gas molecules will collide. Two gas molecules will, if they're this far apart, they'll collide at the length of this room, the width of this room. Okay? That's how far they'll travel before they collide. Liquid molecules, on the other hand, they're touching. The forces between them are weak and they can move about. So if you have a drop of water, if you have a molecule of water, you don't know where it'll be 3 seconds later. In a solid, if you have a molecule, it'll stay there. You can come back 10 years from now, it'll still be there. Okay? So in a solid, the forces between molecules are stronger than in a liquid. But both in a solid and liquid, they're touching each other. But in a liquid, the molecules can travel around. Yeah. All right, so cells and organisms are filled and surrounded by fluids, okay, whether air or water. Larger plants and animals have developed circulatory or vascular systems. Okay, why do you have a vascular system? Why do you have a circulatory system? Why do you have blood and all that? Okay, yeah. So ultimately, a cell, how does it get its nutrients and oxygen? Via diffusion. Okay, that's how stuff is given to the cell in the final analysis. But what's the problem with diffusion? It's not fast enough. It only happens slow. So that's only the last mile. But if you're bringing in oxygen from here, if you're bringing in oxygen from a far off spot, then you have to transport that. And that's what the job of the blood is. Okay? So as soon as you become large, you have to have a circulatory system, a complex circulatory system. Okay? All right. So large plants have developed vascular systems that use fluids. So you're using some kind of fluid to transport the oxygen and nutrients. So your nutrients and oxygen mix in your blood, and that's how they're transferred. Okay? And how does diffusion happen? In what direction does diffusion happen? Which way does diffusion happen? Higher to lower concentration. So if you want to transfer something from here to there, that stuff had better be in higher concentration there and there. Okay? So when you're transferring oxygen from blood to cells, oxygen is at a higher concentration. And then what are you doing in reverse? You're transferring carbon dioxide from cells to blood. Okay? So that's at a higher concentration. All right. So the physics of fluid makes spectacular demands on organisms. So, is there anything that breaks the laws of physics? No, you can't break the laws of physics. Okay, so there are laws of fluids, and so all organisms have to obey the laws of physics, fluid. And so they had to, so creatures have evolved to structures to comply with the laws of physics, with the laws of fluids. Okay. The proper functioning of alveoli in the lungs depends on smooth airflow into and out of the lungs. All right, so here's, we'll talk about this in more detail later, okay? So here's an alveoli. An alveoli is Okay, you guys all know alveoli. I'll show you. Those are the smallest things, that balloon-like structures in your lungs. Okay. Okay. So there's an alveoli, and it's surrounded by blood vessels, and so oxygen diffuses into the blood vessel, and carbon dioxide from the blood vessel to there. Okay. Now here's the amazing thing about alveoli. They're like a rubber balloon. Okay. So if the rubber balloon is stiff, it's harder to blow it up, right? And if it's too soft, what is the problem? You blow it, it could burst. Very good. So the body's got to solve this problem. You got to make it easy enough to blow it up, but you got to worry about it not bursting. All right. So what do you want to do to make it blow it up? Make it. You got to make it soft. But if you start off with the soft alveoli, well, what you blow it up, then it's going to burst. How are you going to fix that?
I don't know. I think of a balloon, usually like a latex balloon, you give it a little stretch first before you put the air in, and that helps to kind of soften them.
Okay, so every time you're taking a breath, you're going to go stretch your alveoli?
Yeah. Well, I mean, it's shallow breaths, stretch it open.
No, so you guys understand the problem? So you got to make that stretch variable. So you know what happens to your alveoli? Initially, it's easy to stretch, and as it gets bigger, it gets stiffer to stretch. It gets stiffer. So how does that happen? We'll talk about that. All right? And remember, so when you're breathing out, if it's too stiff, it might collapse. So it's got to get softer. So when it's small, it's softer, and when it gets bigger, it gets stiffer. Okay, some babies are born where they have trouble breathing, and that's because their alveoli they can't become soft, and so have trouble breathing. And it's a fairly common problem, apparently. Okay, and so we'll talk about that. Okay, so how do you fix that kind of problem? So, and you can't have one being soft compared to other alveoli. So it would require, okay. Finally, one alveolus becomes larger. If one alveolus becomes larger than other, it would require less pressure for further inflation. It turns out that if the stiffness didn't change, if your body didn't have this mechanism, if one alveolus was bigger than the other, and if the stiffness didn't change, then you're blowing air. This would just blow more and burst, and this would, okay. And if you didn't make the stiffness change, you should have to make sure that every alveolus was the same size. You have 500 million of those. It's amazing design. Okay, so hopefully, we'll talk about this. So these problems are avoided in healthy lungs by something called a permanent pulmonary surfactant. Okay, this is what makes alveoli soft, and if you have less surfactant, then it'll become. So we'll talk about that. Oh, that was slide 50. So that stuff is coming a little down the road. All right, so fluids are gases and liquids. Okay, so life depends on fluids, blood flow through our bodies. Cellular processes operate within the intracellular fluid. So your cell is filled with fluid, and all the processes happen in fluids. Okay, so you want to understand fluids. We breathe air, and aquatic animals live in water. A fluid is a substance that flows. Anything that flows is fluid. Liquids and gases are fluids. Okay. All right, so in a gas, there's a lot of space between molecules, and the only time they interact is when they collide, okay? And otherwise, they're not, the forces between them are negligible. Liquids, on the other hand, there's a strong bond between them, but the bond between these molecules is not as strong as in a solid. In a solid, it's stronger, and in a solid, all the molecules are in fixed locations, okay? You can come back 10 years from now, and as you heat a solid, it might vibrate about its position, but it's not leaving its position in a solid, the molecules, okay? In a liquid, the forces are weaker than that, and they can move about. But again, you can't compress a liquid either, okay, because there's no space between them to squeeze out the, there's no space between them to squeeze. Okay, a gas is compressible. What do you mean by compressible? You can decrease its volume. Why is it easy to decrease its volume? Because see, all this empty space. Okay, so you can decrease the volume of a gas. In a liquid, the molecules are bound to each other, though less strongly than in solids. The weak bonds keep the molecules close together, but allow them to move around. Okay, so a molecule in a liquid is always moving about. It's free to move. Okay, and higher the temperature of the liquid, the faster they can move. Okay. Liquids, like solids, are incompressible. Okay, there's no gap to space between the molecules to squeeze them up. So the first thing we'll define is density. Density is denoted by rho, the letter rho. It's a Greek letter. Yeah. And it's defined as mass divided by volume. Okay, and it's a property of the material. Okay, so the SI units for it are mass is measured in kilograms, distance in meters, the volume is meter cubed. Yeah. Now here's the things. So let's say you have several pieces of, you have a block of copper, and then you break the block up. You have several pieces of copper. The mass of each piece and the volume of each piece is different, but the density of all the pieces is the same. Okay? So suppose you have you have several blocks of copper, each of different size. Each block has a different mass and different volume. However, the ratio, mass to volume, which we call the density, is the same for each block. So density is a property of the material. Okay. All right, now let me give you the density of gases, liquids, and solids. Okay, so for air at 0 degrees Celsius, the density is about 1.3 kgs per meter cube. Okay, so here are the meter cube. This much air is a meter cube. So this much air weighs 1.3 kgs, which is about 3 pounds. That much air weighs 3 pounds.
You're saying inside that desk?
Yeah, so if you take this, yeah. That much water weighs about 2,500 pounds, 1,000 times more. Okay, so this much water weighs as much as a small car. This much iron would weigh 10,000 kg per meter cube, 10 times as much. All right, so the density of a liquid is 1,000 times greater than the density of a gas. The density of a solid is about 10 times greater than the density of a liquid. Okay, I mean roughly. That's what it means. Okay. So what that means is, if in a gas, molecules are this far apart, in a liquid they're touching each other almost, and in a solid they're twice as close. Okay, 1.5, twice as close. Yeah. Okay. So that's what that means. The closer you are, the higher the density. Okay.
So solid is approximately 10
Yeah, 10 times, yeah, 10 times more dense.
The fluid?
Mm-hmm.
Or liquid?
Yeah. So ballpark, I mean specific solids. So mercury, lead is one of the densest material. Titanium is denser, I think. Okay. All right, all liquids, all fluids exert pressure. Okay, pressure is force per unit area they exert. And here's the thing about fluids, they exert a pressure always perpendicular to the surface. Okay, so this water is exerting pressure against the wall like that, against this wall like that. And in addition, they exert pressure against each other. So let's say you're looking at this block of water, liquid, and this block of liquid. This block is exerting a force in that direction, and this block is exerting an equal and opposite force in that direction. Okay. So whatever surface you draw, they're pushing perpendicular to that surface. Okay. So pressure is defined as the force exerted per unit area. Force is measured in newtons and area in meter square. This is the SI unit for pressure. And this unit is called a Pascal, after Mr. Pascal. Okay, all units in physics are named after scientists. Okay, so this was Newton is named after Mr. Newton. So this is Pascal.
It's
Newton per meter squared.
Meter squared.
Yep. All right, let me show you how a gas exerts pressure. Do you know how much is 1 atmospheric pressure? How much is 1 atmosphere?
Our atmosphere,
Mm-hmm.
you said it was 1.29?
No, that's the density of air. Yeah. The pressure, 1 atmosphere, is, you guys, after I tell you, you'll know it, about 15 psi. Okay. It's in pascals, it's 10 to the power 5 pascals, Newton per meter square. And you might know this as 760 millimeters of mercury. And we'll understand all these different units of pressure. But I want to make a point on this thing. What is PSI? Anybody know what is PSI? Pounds per square inch. So here's a square inch. Okay, so what does 15 psi mean? Air is exerting a force of 15 pounds on every square inch. Air. Do you feel the air molecules hitting you? They're exerting a force of 15 pounds per square inch.
That's a lot.
That's a lot. Well, you want some? Rip me a piece of paper. All right. This piece of paper, it's 15 pounds per square inch. Every square inch, the air is pushing with a force of 15 pounds. This is 10 inches by 10 inches. That's 100 square inches. So 100 times 15 is 1,500 pounds.
Which is wild, because if you put a 15-pound dumbbell down on any part of your body, you're really gonna feel it.
That's
So
right.
funny.
It's, you tell me I'm lying to you. 1,500 pounds. There's a force of 1,500 pounds on this paper. Why isn't this flying away?
Gravity helps.
It's on both sides.
It's on both sides. Exactly. You want to see that 1,500 pounds? Who wants to get rid of a pencil? I need a pencil. You won't get it back.
Oh,
I mean, I have a pen, I don't like, I don't use that.
No, I need a pencil. All right. You you 1,500 pounds, I'll show you 1,500 pounds. I don't like this stuff. I can't think if it's like that. All right, so you think I can break this pencil? So what is needed to break this pencil? You need a fulcrum, and I need to apply force like that, and I need to apply force there. Okay? That's how I break the pencil. And I could break it down. How about now? So I'm going to demonstrate my karate chop. Okay? You think I could break it like that? Will it break?
Well,
Why
not
not?
now, it'll just flip
It'll fall
off.
off the table because the pressure's only on one side.
Okay, so there's only force on one side. Yep. All right.
Rip my paper.
All right. I need a softer paper and a longer pencil.
It's really my stuff.
Yeah, you need a longer pencil. We'll give it one more try.
This paper's pretty thin too.
Huh?
This paper's really thin too.
This has the, that one? Okay. Oh, there you go, that's it. Thank you. All right, so 1,500 bucks.
Broke.
And the paper didn't move.
So what's going on?
Pressure.
So here's what was going on. See, when I hit it on, there's 1,500 pounds. When I hit that paper, if air could get underneath there, then it would apply 1,500 pounds. But it happened so fast, air couldn't get underneath there. 1,500 pounds held it. So this paper was waxy and it had an opening like that, so that would work. Here's the pencil back. All right, so you saw that there's 1,500 pounds on this sheet of paper. Imagine the force on your body. Okay? Your front side of your body is 100, probably about 1,000 square inches. There's 15,000 pounds of force pushing you back.
But there's 15,000 pounds.
That's right.
of force pushing the floor.
You don't even think about that. Yeah, that's why you can move around in the fluid. There's equal forces on you on all sides. Okay? If there wasn't, you hold your arms on the table, there's a force, large force on you on your arm. And no reason you're able to lift it, then equal and opposite force.
That's why the blobfish blows up when you pull him out of the water.
Yep.
Because his body needs that force.
So you go underwater. Well, right now, why aren't you collapsing? There's a great force on you. There's an equal and opposite force from inside. Okay, so the pressure inside. We will talk about this. So right now it's 15 pounds per square inch. If you go 10 meters underwater, twice this depth, 33 feet underwater, now the pressure increases on you to to 30 psi.
And that's why organisms can only go so deep in the water without getting crushed.
So what do? When you go diving, now you're breathing air at 2 atmospheres. When you go 66 feet underwater, what do you have to do? Breathe air at 3 atmospheres. The higher the pressure you breathe air at, the more of that air mixes in your blood. And if you come up too fast, if you come up high too fast, it'll all bubble into your joints and stuff like that. And that hurt. Yeah, that's the bends. Okay. All right, so we were going to look at okay, so you see the pressure of this gas is 30 atmospheres. So 1 atmosphere is 15 psi. 30 times that is 450 psi. These air molecules that weigh nothing are exerting a force of 450 pounds every square inch. How are they exerting that force? By bouncing off the walls, okay? And so they're bouncing off billions of times. There's billions of collisions happening, okay? And that's how they exert the force. And I'll show you a demonstration on, you already saw on the air pressure, but I'll show you another one in a second, okay? So that's how air molecules exert pressure. Now, let me do one more thing. Okay, watch this. Okay, the temperature decides how fast the molecules are moving. So now I'm going to keep the temperature constant. I'm going to add more gas molecules. What will happen?
Temperature should go up.
See, the temperature is constant.
They're going faster?
Well, the temperature decides how fast they're going on the average. They're going at the same, on the average, they're going at the same speed. Why did the pressure go up?
Because there's more molecules. They're
So?
taking up more space.
There,
More force within them.
there's more collisions happening. Okay? So the pressure depends on the density. Okay. So how many collisions happen is the issue. Okay. All right, so here's one of the units for pressure, pascals. Okay. Now, in a liquid, we'll learn as you go deeper, the pressure increases. And the greater the pressure, here, outside the pressure is 1 atmosphere, the greater the speed of the molecule. The greater the speed at which the jet comes out. All right, you can see that there's greater pressure, this jet comes out faster and it goes further. Now, this is going the same distance as that because this has less time to travel, so they hit the same spot. But anyway, so the faster it'll come out, the liquid. In fact, if the viscosity is negligible, this won't be true for honey, but for water, it's roughly true. Here's an amazing part. If you drop a keychain from here to there, you know how fast the keychain will go. Okay? The water is actually coming out at the same speed as that. Okay? So it's like dropping water from there to there. Okay? So pressure in a fluid increases with depth. So here's our atmosphere. Our atmosphere, the density decreases exponentially. Okay. In fact, if you go 5 miles up, you have crossed half the air. The first 5 miles, so space is considered up to about 60 miles. Okay. If you go 60 miles up, and the density becomes almost 0. But it decreases so fast. If you go 5 miles up, this 5 miles has the same mass as this 55 miles. Okay? So you've crossed half the atmosphere if you climb up 5 miles. Okay, so you just saw a second ago, the greater the number of the molecules, the greater the pressure. So the pressure also decreases with height. Okay. In fact, in Denver is a mile high, I guess, 1,600 meters high. The pressure is 83% of that on sea level. Okay. So in Denver, you're operating with 83% of oxygen. Okay. So, so one standard atmosphere is 100,000 pascals. Okay. So here are the various units for pressure. 1 atmosphere is that is 100,000 pascals. It's also about 15 psi and 760 millimeters of mercury. Okay. In the healthcare field, you measure all your pressures in millimeters of mercury. So when you say your blood pressure is 120 by 80, that's 120 by 80 millimeters of mercury. 120 on the systolic pressure, and 80 is the diastolic pressure. Okay? And we'll talk about that. The atmospheric pressure at sea level varies slightly with weather, but the global average pressure is 100 kilopascals. Okay. Now you saw that, we saw that why you can walk around in air, even though on the front of you there's probably 15,000 pounds of force pushing you back. That's because air in the back is pushing you with a force of 15,000. Okay, so that's what fluids exert pressure perpendicular to the surface, and they exert in all directions. Okay? So you might wonder why the weight of air doesn't crush your forearm when you rest it on a table. Okay, so the force on your forearm when you rest it on a table is, so this goes through the calculation. I'm not going to go through the calculation. So pressure is force times over area. So force is pressure times area. And the pressure, atmospheric pressure, is that many newtons per meter square. This is the pascal. And the area of your forearm is 200 centimeters square. 200 centimeters square is about, I'm sorry?
2 square meters?
No, 0.02 square meters.
Oh.
Yeah. Well, I was, and so we'll borrow 2 of those, make it 10 to the 3. 100 times that is 2, so that's 2,000 newtons. And this is 450 pounds. Okay, so when you're resting your forearm, when you hold out your forearm, the force that the air is exerting on your forearm is 450 pounds. 3 people sitting on your forearm. And the reason you're able to lift it up is because there's equal force there. Okay, there's equal force there. But if I rest it now, well, there doesn't seem to be any air underneath my forearm. There is. If there wasn't, your forearm would get crushed. Okay, whatever little air there is, that's pushing it up. Okay, and we'll illustrate that.
Because as smooth as this looks, it's not really smooth.
Right. So that's because fluid exerts a force in all directions. There's a downward force on your forearm, but the air underneath your arm exerts an upward force of the same magnitude. Okay. The fact that we are surrounded by fluid allows us to move around in air just as we swim underwater, oblivious of these strong forces. Okay. Fluid pressure inside your body is very close to 1 atmosphere, and it prevents you from imploding or exploding. If it was more than 1 atmosphere, if it was 2 atmosphere, you would explode. And if it was less than 1 atmosphere, you would implode. Okay? So when you swim underwater, the pressure has increased, and so your volume slightly reduces imperceptibly because you are compressed. when you're compressed, and then the internal pressure increases to 2 atmosphere, and then you're in equilibrium. Yeah. Okay. So here's a problem. You might have heard of Alvin. Alvin is a research submarine. It's a small submarine that goes. So the average depth of ocean floor is about 2.5 miles. Yeah. 4 kilometers. Okay. So if you go every 10 meters, the pressure increases by 1 atmosphere. Okay. So if you go to about 4 kilometers, 4.5 kilometers, the pressure increases by 450 atmospheres. That is about 7,000 psi, pounds per square inch. That's an enormous force. Okay. So this is a research submarine. It's underwater. You want to study animals. You want to study things. You can't look through metal. You have to have windows. Okay.
Is that one of the things they use as sapphire for the windows?
I don't know what the material they use,
For
but
the
here's,
space shuttle, they used a sapphire for the windows because glass wasn't strong enough.
well, one of the other things you have to worry about is you don't want heat conduction. So it has to be clear and not conduct heat, because when you're re-entering, everything heats up to red hot. So, but here we'll talk about the design of the windows. So you want to have windows. Now here's a side view of the windows. Okay, you're experiencing forces of 7,000 pounds per square inch. You don't want that window cracking. Takes too long to come back up. So this is how the windows are designed. It's a conical shaped hole, and you put the window there. The harder the water pushes, the tighter your seal gets. Okay. So you just got to make sure there's no defects on the window. Okay. So installing a window in a craft that goes to this depth is no mean feat. Okay. So this is a technician inspecting the window that'll fill the viewport. A tapered shape will have its larger face outward toward the sea. The water pressure will push the window firmly into its conical seat. All right, now we'll demonstrate atmospheric pressure forces. Okay, so here is a suction cup. Okay, what does the suction cup do? What does it do? I mean, we've all used a suction cup. What it does is it removes the air from behind there. Now, if there's no air inside back there, so, okay, if I put my arm here on the table, if there's no air underneath there, what is the force on my arm? 450 pounds.
Only in one direction.
Only in one direction. That's the idea. You remove air from that. Okay. You might have seen bicycle racks with suction pumps. I had one of those. And the suction surface is about that much. You can drive with a bicycle on that at 80 miles an hour. You've not seen this? You gotta see, what are those things called?
I would not trust it.
I know. I've seen the sections.
Like, I would still put it down as something that's bolted in.
There. So that's, you just clamp it onto your car. All right, so let's look at those forces. Okay, so here's a suction cup. The area of this thing is 10 centimeter diameter, so it's about that big. It's roughly the size of your palm. Okay, so you're going to put this suction cup and attach it to the ceiling, and let's see how much weight you can attach to the suction cup. So how's this working? You've removed all the air there, and the air is holding this up. Okay, so the force of air is holding this up, and that's supporting the weight. Okay. How much weight can you hang there? From a suction cup the size of your palm, you can hang 81 kgs. 81 kgs is 180 pounds. So a 180 pound person can hang on if a suction cup is in. The slightest bit of air leaking in, nothing is coming out. Okay. All right, now we'll look at pressure with depth in a liquid. Okay, so here's, let's say, water. Here, let's say this is a tank of water. There's atmospheric pressure pushing you down. And then if you're at this depth, you have to support this weight as well. You have to support this force and the weight of this liquid column. Okay? So let's say you're at depth D. So again, pressure is force times area. So the force is pressure times area. Okay. Now, atmospheric pressure is denoted by P naught. Okay. And so that force, the force you're having to support, downward force is P naught times area. P naught times area. And the weight of this liquid column is the density of the liquid times the area of cross-section times depth. The density of the liquid times area times depth times G and times G times height. Oh, I got the depth there. So that's the depth. Yeah. And that should equal this upward force, which is P times area. And you see the area cancels. Okay. So the pressure at a depth is P equal to P naught plus rho dG. P equal to P naught, the atmospheric pressure, plus the pressure due to this liquid column. And if you put the density of water in 10 meters, you get another atmosphere. So for every 10 meters deep, for every 10 meters, this will equal that. Okay. So the deeper you go in water, the higher the pressure. Okay. So like I said,
Is that last P the same as the first two?
and this is P,
Different symbol.
that's rho.
Okay.
Okay. So this is pressure at depth, this is atmospheric pressure. Rho is the density of whatever fluid. Okay? All right, so so here's an issue that comes up. Okay. So you just saw that as you go deeper in water, the pressure increases. So let's say you're swimming underwater at a depth of 5.5 meters. That's what this calculation is. 5.5 meters is roughly the height of the ceiling here. So if you're this deep underwater, okay, here's your eardrum. Now the pressure is pushing you harder. Your eardrum is harder. And you don't want your eardrum to get damaged. How will you make sure? Okay, what's happening now? Why is you're not feeling any force on your eardrum? The air is exerting a force, quite large force on you. Why aren't you?
Because our internal pressure is about the same as our.
That's right. So now let's look at the side view. There's the eardrum, and I'll attach you to it. So here in the inner ear, there's air that's balancing this pressure. Okay. What is the pressure in here? 1 atmosphere. Now, this is an enclosed area. When you went down, that pressure is still 1 atmosphere. But this pressure increased because you were underwater. And so now you had an extra force on this guy. Okay, and that's what this calculation is about. So when you were underwater, the pressure underwater is that, okay? And and the diameter of your eardrum is 8 millimeters. So that's how big your eardrum is. The force of the water on your eardrum is 8 newtons. 8 newtons it's about 2.5 pounds. It's 2 pounds. 2 pounds is sitting on your eardrums.
On your itty bitty eardrum.
On your itty bitty eardrum. And it's very thin membrane. Remember, air has to make it vibrate. Okay? Well, there's 1 atmosphere trying to save you. So what is that force? The 1 atmosphere is trying to save you, and that's about 3 newtons. Okay? So no, that's about 5 newtons. So the net force on you, the water minus the air, is 3 newtons. But that's still painful. How do you fix that?
Somehow you gotta balance out the internal pressure with the external.
How do you do that?
No idea.
So, all right, so there's air in your lungs now at the higher pressure because you got compressed. The air is at a higher pressure. Well, this inner air is connected by the eustachian tube to your throat. Now, this eustachian tube is generally closed, so this is not an extremely, okay. However, divers go deeper than have to learn to equalize the pressure inside the ear with the external pressure. They do so by pinching their nose and blowing gently to force open the normally closed eustachian tube. So you close your tube and you blow gently. Okay. So the air at higher pressure in your lungs, you blow that in there, and now the pressure is equal. Okay. So there are cultures where they free dive to quite a larger depth, and so they naturally do it all the time. Yeah. All right, is this possible? So in a liquid, at a given level, the pressure is the same. Okay, you saw that the pressure is given by the atmospheric pressure. If you're open to the atmosphere, you have atmospheric pressure plus the pressure due to the depth. Okay, so for a given depth, the pressure is the same. So would this be possible? This won't be possible because at this level the pressure would be higher than here, and so higher pressure will force the liquid in this direction. So if you have open containers like this, liquid will always be at the same level. So this is not possible, and this is possible. Okay, so now we'll.
As a kid,
Huh?
at the flea market, they have these, sometimes they made it look like a bird, sometimes it was just balls, but there was liquid on one side, and you squeeze it, and it would go to the other. You just squeeze the glass ball, so you're not actually like crushing anything, and then the liquid would move.
No.
Now I know how that works.
All right, so gauge pressure. And part of the thing is also in that thing, your hand is warming, and it's the liquid is an alcohol or something. Enough alcohol vaporizes, and that increases the pressure. So I'll remember and bring a similar toy next time. All right, we'll define gauge pressure. Most of the gauges that you use, they don't measure the actual pressure. The actual pressure is given by P. What they measure is the actual pressure minus atmospheric pressure. Okay? Atmospheric pressure or P naught, or whatever you want to write it. Okay? So we define something called a gauge pressure. Okay? That's what you mostly measure. So the blood pressure that you measure, 120 millimeters of mercury. That's actually gauge pressure. So your systolic pressure is really 120 plus atmospheric pressure. That's 880 millimeters of mercury. That's the actual pressure. But you know, if you told patients that, nobody will come to your office and you're not making money. Right, so a lot of the pressure that we talk about in the healthcare industry is gauge pressure. Okay? How much above the atmospheric pressure is. So gauge pressure is actual pressure minus atmospheric pressure. What is the pressure in your car tires?
Usually about 35.
So
PSI, yeah.
30 psi, that's a gauge pressure. So the actual pressure really is, this is 30 psi. So 30 plus 15, 45 psi is the actual pressure in your tires. Yeah. So a barometer is something that measures atmospheric pressure. Yeah. And here's how you make a barometer. So you take mercury in this tube, fill it up with mercury, you hold your thumb like that, and then invert it in a mercury bath. Okay. And then what will happen is this liquid will come to there. This will be just about the perfect vacuum you want. Okay. And the height of this column is 760 millimeter of mercury, if mercury is what you use. And that's where that atmospheric pressure comes. Okay? The height of this mercury column, 760 millimeter is 76 centimeters, or 0.76 meters of mercury. It's about this high, a little over 2.5. It's close to 2.5 feet. Yeah. Now, if you made a barometer with water, the height of this column would be 10 meters, 33 feet. Okay, so that's why, of course, you don't make barometers with water. You have to have a dense liquid. All right, what is going on is the following. This weight of mercury is being balanced by a column of air all the way to space. So this column of air is balancing this weight of mercury. Okay, so it's like putting, this is a balance, and this column of air of equal area of cross-section is balancing this column of mercury. Okay. Okay, so the pressure due to that column of mercury is rho, the density of mercury, G times H, the height. So higher the density, smaller the height. So if you use water, this would be 10 meters. If you use mercury, this is 76 centimeters. All right, so again, this column of air all the way to space can balance 76 centimeters of mercury and 10 meters of water. Okay, so this pressure due to air going all the way to space, has the same weight as 10 meters of water, has the same weight as 76 centimeters of mercury, all of the same cross-section. All right, so we are going to use this in this hand pump. Have you guys seen this kind of hand pump? Has anybody used them? You used them? We're camping.
No, grandmother's house
Mhm.
Was around before plumbing,
Mhm.
and in her front yard for her water hose, there was this.
Very cool. So here's how it works. Okay, so this hand pump, you have a diaphragm like that. And what you're doing is when you pump down, the diaphragm moves up. And what happens? You create a vacuum there. There's no vacuum, there's no air pushing you down. And this atmosphere will push water up. So if you create a perfect vacuum, that is, if you have a good hand pump, a bad hand pump doesn't create perfect vacuum. If you have a good hand pump and you create perfect vacuum, this air can push the water up 10 meters. 10 meters is twice this depth, twice the height of this room. Okay, so that's the maximum depth it can work at. So if your water table had better be within 10 meters of where you want to pump the water. Okay. So here are some of the pressure units. Pascals is the SI unit for pressure. 1 atmosphere is our atmospheric pressure. Millimeter of mercury, this is what's used in the healthcare industry. So for instance, when you go to your doctor and your ophthalmologist measures your ocular pressure, you guys know that number? It's about 15 psi. 15 millimeters of mercury. So inside your eyeballs, there's about 15 millimeters of mercury of pressure. Okay, and that's a gauge pressure. So why do you have that high pressure?
To hold its shape.
Yeah, hold its shape. Okay, and yeah. So so in practice, pressure is measured in different units. These units arose historically as scientists and engineers worked on different subjects, developed units convenient to them. Okay. So these are the units: pascals, atmospheres, millimeters, and psi. Those are the 4 units that we will encounter generally. Okay? All right, I'm going to get up to slide 29. Okay. All right, so in this thing, which is possible? Oil is less dense than water. And in a liquid, if you're at a depth H, the pressure is rho. The pressure is rho G H. H is the height of the liquid. So lower the density, lower the pressure.
Okay, but so C?
Yeah, so A is not possible because you want the same pressure at this level, and this oil would exert less pressure than that, and so this would push this liquid that way. This is not possible, again, because oil exerts less pressure. This will push it up. C is the correct answer. Okay? Now we'll talk about buoyancy. Okay. So if you immerse some object underwater, you will feel an upward force. And this is a buoyant force. Why do you feel an upward force?
Is there air in us?
No.
So there's gonna be less density. We're not completely liquid, so there would be less density in us than there is in the atmosphere of the water.
All right, so we learned that pressure increases with depth of the water. And the greater the pressure, greater the force. So the water is exerting a downward force on us. But the pressure at a greater depth is greater, and so there's a greater upward force on us. So because the pressure is increasing with depth, there's an upward force, greater upward force, and the net force is the buoyant force. That's what's pushing you up. So if you go deeper, the pressure is increasing with depth, and that's what's causing the buoyant force. So let's say if you build if you build a swimming pool in space, this won't be true anymore. Okay, there's no pressure increase with depth. Okay? If you're far away from a gravitational field, and then you won't feel a buoyant force. All right. So the pressure in the liquid exerts a net upward force, and this is the buoyant force. Okay? The basic reason for buoyant force is straightforward. The pressure in the liquid increases with depth. So the pressure at the bottom of the cylinder is greater than at the top. Okay? And so the force at the bottom is greater than the force at the top. Okay, Mr. Archimedes figured out how large this force is. What is the exact value of this force? Okay? And so that's why we still talk about him 300 years later. Okay. The magnitude of this force is equal, so this object displaced that much water or that much liquid. The magnitude of this force is equal to the weight of that much liquid. Okay? So if you displace 10 pounds of water, the upward force on you is 10 pounds of water. Okay? Now it turns out that, so let's say, so when you weigh yourself on a scale, so let's say when I stand on a scale, okay, Earth pulls me down with a force of about 165 pounds, give or take a few pounds. And the scale has to push me up with a force of 165 pounds. That is your apparent weight. That's the weight you feel. You don't feel this force of gravity. You feel this force that's pushing you up. All right, now we'll do the same thing. So I'm going to do the same thing underwater. Okay, so under the swimming pool, go ahead.
You're not going to weigh anything.
That's right. So gravity never quits, unfortunately. It's pulling me down. But the water is pushing me up. The buoyant force is pushing me up. And so now the normal force has to be small, because normal force plus buoyant force equal to my weight. These two forces have to add up to equal to my weight. Now this is almost equal to that. So underwater, this force is zero. You're weightless. Okay? Our density matches the density of water almost exactly, and so this force, the buoyant force, is equal to your weight. So underwater, you'll be weightless. Okay? Anyway, the buoyant force is equal to the weight of this water, okay, of the displaced fluid. The magnitude of the buoyant force equals the weight of the fluid displaced by the object. All right, so let's figure this out. So which one will feel the greatest buoyant force? So here's this object, this object. Which object will feel the greatest buoyant force? Okay, so the volume of this is 10 centimeter cube, 10 centimeter cube, 10 centimeter cube, 20 centimeter cube. This is displacing the greatest volume of water. So that will feel the greatest buoyant force. The mass of that object is just to distract you. That's not relevant to the problem. This is feeling the greatest buoyant force. This is feeling the smallest buoyant force. Yeah. So I've changed this diagram in the new notes, but the question is what will float and what will sink? Okay. For an object to sink, the object's density has to be greater than the density of the fluid. If the object's density is equal to the density of the fluid, it will hover. It will neither sink nor come up. And if the object's density is less than the density of the fluid, it will float. It'll rise up. Okay? So it's the relative density that matters. If the object's density is greater than the density of the fluid, then it'll sink. If it's less, it'll rise up. And if it's equal, then it'll hover. So for an object to float, the object's density has to be less than the object's and than the fluid density. Yeah. All right, so let's say this object is floating. Okay. Now what we want to know is what is the volume underwater. Okay, Mr. Archimedes told us that the buoyant force, he told us exactly how much this buoyant force is. What is the buoyant force equal to? It's equal to the weight of the water displaced. How much water was displaced? This much water was displaced. Okay, so this force is equal to this much water displaced, but this force is balancing the weight of the object. Okay, so here is what this formula tells you is the volume of the fluid displaced is equal to the density of the object divided by the density of the fluid times the volume of the object. All right, since this object is floating, this is smaller than that, so this gives you the fraction of the body underwater. Okay. Now let's do this for icebergs. For iceberg, the density of this object is 917 kg per meter cube. The density of the fluid, seawater, is that much. Okay. So the volume of the iceberg underwater, the volume of the water displaced, is equal to the density of the iceberg divided by the density of the fluid times the volume of the object. And that is 90% the volume of the iceberg. So 90% of the iceberg is underwater. Okay. Every shipping captain knows this. The Titanic shipping captain knew this. He knew not to go close to the iceberg because you don't know what is underwater. Okay. So that was a rookie mistake that somebody made. A rookie mistake made by a captain who was captain of the most expensive ship.
Most human failures can lead back to fear or arrogance.
So how does a boat float? Here's the weight of the boat. And if you want it not to sink, you want an equal and opposite buoyant force. And so you put a boat in water, it sinks to the level such that the weight of this water is equal to the weight of the boat. So
Don't you put a little weight in that tip at the bottom?
the keel is heavy. That is to keep the boat stable. If you come to this side of if all your buddies come to this side of the boat to watch a whale, you don't want the boat to tip over. Okay, so if you come here, the keel will come over here, and the keel is counterbalancing. Okay. So the keel is heavy to not tip over. Okay, so how far does the boat sink such that this water is equal to the weight of the boat? Okay. And so if you invite some friends, now the boat will sink further such that now the new amount of displaced water is equal to the weight of the entire boat. All right, so we'll stop here.